Hello my friends and welcome back to Sky Creative Channel. Today we're taking you on an incredible journey, from massive crankshafts that power ocean-going vessels to precision railway components that keep millions of commuters safe. So grab your coffee, settle in, and let's dive into the fascinating world of industrial manufacturing. Here we are at Alphen Kessler, witnessing something truly spectacular, the machining of a massive marine crankshaft that weighs over 15 tons. This isn't your everyday workshop project, folks. These crankshafts are the beating heart of container ships and cruise liners, converting the explosive power of diesel engines into the rotational motion that propels these maritime giants across our oceans. NNTHE star of this show is Alphen's revolutionary vertical turning and boring machine, standing nearly 3 stories tall. This engineering marvel features a 6-meter diameter faceplate capable of handling workpieces up to 20 meters in length. The machine's spindle delivers an impressive 200 kilowatts of power while maintaining precision tolerances of just 0.01 millimeters. That's thinner than a human hair. The advanced CNC system coordinates up to 12 simultaneous axes, ensuring every cut is executed with mathematical precision. No rotch as the massive crankshaft rotates at a carefully controlled 15 RPM. The carbide cutting tools, each costing more than a luxury car, slice through the hardened steel like butter. The coolant system pumps 500 gallons per minute of specialized cutting fluid, preventing thermal distortion while washing away chips that look more like metal ribbons. Notice how the operator monitors vibration sensors and thermal cameras. At this scale, even tiny variations can spell disaster. NNTHE real magic happens in the finishing passes. Using diamond-tipped tools, the surface finish achieves an incredible raw 0.4 microns, smoother than a mirror. Laser measurement systems continuously verify dimensions, while ultrasonic testing ensures the internal structure remains sound. This single crankshaft will operate for decades, generating millions of horsepower cycles. It's a testament to German engineering precision that transforms raw steel into a mechanical masterpiece worth over $500,000. Welcome to Radadiyya Industries, where they've redefined what heavy-duty really means. This isn't just another CNC lathe. This is a mechanical monster designed to tackle the roughest, toughest machining challenges in heavy industry. When aerospace manufacturers need to machine titanium landing gear components, or when power plants require custom turbine shafts, this is where they turn. This beast boasts a swing diameter of 1.5 meters and can handle workpieces up to 12 meters long, weighing as much as 25 tons. The main spindle generates 300 kilowatts of power through a precision planetary gearbox, providing tremendous torque at low speeds. The machine bed, cast from high-grade mehanite iron and stress-relieved for 6 months, provides the rigid foundation necessary for such demanding operations. Watch as the machine attacks this massive steel billet with aggressive roughing cuts. The cutting parameters are mind-boggling. 15 millimeters depth of cut, 0.8 millimeters per revolution feed rate, removing over 200 cubic inches of material per minute. High-pressure coolant jets, pumping at 1,000 psi, blast away the continuous ribbons of steel chips that could fill a pickup truck bed in just minutes. And advanced vibration damping systems and thermal compensation ensure dimensional accuracy within 0.05 millimeters across the entire workpiece length. The CNC system, featuring adaptive control technology, automatically adjusts cutting parameters based on real-time force and temperature feedback. It's like having a master machinist's intuition built into the machine's brain. Step into the world of railway wheel manufacturing at Railteco, where safety and precision aren't just priorities, they're matters of life and death. Every day, millions of passengers trust their lives to these wheels, which must endure tremendous forces, extreme temperatures, and millions of rotation cycles. From high-speed trains screaming through European countryside to heavy freight locomotives hauling across American plains, the wheels we're about to see represent the culmination of over 150 years of railway engineering evolution. Our journey begins with carefully selected steel billets, heated to a blazing 200 degrees Celsius in massive induction furnaces. Watch as the glowing steel is shaped by 8,000-ton forging presses that deliver forces equivalent to the weight of 800 elephants. This forging process aligns the steel's grain structure, creating the incredible strength needed to support 25-ton rail cars. The wheels are then normalized in computer-controlled furnaces, slowly cooling over 48 hours to achieve the perfect balance of hardness and toughness. Quality control begins immediately. Ultrasonic testing reveals any internal defects that could prove catastrophic in service. Now comes the precision work. Each wheel blank is mounted on Railteco's state-of-the-art CNC wheel lathes, German-engineered masterpieces, capable of maintaining tolerances tighter than the thickness of paper. These machines feature massive 3-meter diameter chucks that grip the wheel with hydraulic pressure equivalent to 50 car jacks. The cutting tools are specially designed carbide inserts, each costing $200 and engineered to maintain sharp edges through thousands of cuts. Computer vision systems scan each wheel, creating a 3D map that guides the machining process. Here's where artistry meets engineering. The wheel profile isn't just a simple curve, it's a complex mathematical shape that determines how the train will ride, steer, and brake. Watch as the machine creates the tread surface with its precise 120 conicity, the flange that keeps the train on track, and the intricate root radius that prevents stress concentrations. Each cut is monitored by laser gauges measuring to 0.01 millimeters accuracy. The surface finish must be perfect. Any imperfections would create wear patterns that could derail a train traveling at 200 miles per hour. Before assembly, wheels undergo critical heat treatment. In massive furnaces reaching 900 degrees Celsius, the rim area is selectively hardened while keeping the center section softer for flexibility. This dual hardness design prevents catastrophic wheel failure under extreme braking loads. Magnetic particle inspection reveals microscopic cracks, while eddy current testing verifies the heat treatment depth. Only wheels passing rigorous impact testing, literally being struck with hammers while monitoring the acoustic response, proceed to final assembly. Now for the spectacular finale, wheel set assembly. The axles, themselves precision machined to tolerances of 0.005 millimeters, are heated to exactly 200 degrees Celsius for thermal expansion. Watch as hydraulic presses generating 500 tons of force slowly press the hot axle into the precisely machined wheel bore. As the axle cools, it contracts, creating an interference fit stronger than welding. This connection must survive 40 years of service, supporting loads that would crush automobiles. Real-time monitoring ensures the press force curve matches theoretical predictions. Any deviation could indicate a defective fit. Every completed wheel set faces final inspection that would make aerospace engineers proud. Dynamic balancing machines spin the assemblies at operating speeds, while sensors detect any imbalance that could cause vibration. Ultrasonic testing verifies the axle-to-wheel connection integrity, while laser measurement confirms all critical dimensions. These wheels will travel millions of miles, carrying precious cargo, human lives. The attention to detail we've witnessed today ensures that every journey ends safely at its destination. Welcome to Earl Rolls, where they don't just make pistons, they craft mechanical titans. These aren't pistons for your car's engine. We're looking at massive diesel engine pistons for container ships, power plants, and marine applications. Each one weighs over 5 tons and stands taller than most people. When complete, these pistons will harness explosions equivalent to dynamite blasts, converting that raw energy into smooth, controllable power for some of the world's largest machines. NNTHE journey begins with aircraft-grade aluminum alloy billets, each representing $50,000 worth of premium material. Watch as these billets enter 6,000-ton hydraulic forging presses, heated to 450 degrees Celsius for optimal material flow. The forging process isn't just about shape, it's about creating a grain structure that can withstand pressures exceeding 200 bars and temperatures hot enough to melt copper. Now the real precision work begins on 5-axis CNC machining centers that cost more than most houses. These machines feature spindles generating 100 kilowatts of power while maintaining positioning accuracy of 0.002 millimeters. That's 20 times finer than a human hair. Watch as diamond-tipped cutting tools carve the complex crown geometry, creating the precise compression ratio that determines engine efficiency. The cooling gallery channels, invisible from outside but critical for thermal management, are machined with internal pressures testing to ensure no weak spots that could cause catastrophic failure. NNTHE piston ring grooves demand absolute perfection. Using specially designed grooving tools, the machine cuts these channels to tolerances of 0.01 millimeters. The surface finish must be mirror smooth to prevent ring wear, while the side clearances control oil consumption and blow-by gases. High-pressure air jets blast away aluminum chips that could score the delicate surfaces. Each groove is individually measured using pneumatic gauges that detect variations smaller than bacteria. NNTHE finished pistons undergo rigorous testing that simulates years of operation in minutes. Thermal shock testing cycles them between -40 degrees Celsius and 400 degrees Celsius, while pressure testing subjects them to forces exceeding normal operating loads by 50%. Only pistons surviving these torture tests earn their certification. When installed in massive marine engines, these pistons will operate continuously for decades, each power stroke delivering enough energy to launch a small car. Meet the BMB25 flanging machine by Akyapak Makin, a Turkish engineering marvel that's revolutionizing how we create perfect circular flanges for pressure vessels, pipelines, and industrial equipment. From nuclear power plants to petrochemical facilities, wherever high-pressure systems demand absolute reliability, you'll find flanges created by machines like this beauty. This isn't just metal forming, it's precision engineering that ensures safety in some of the world's most demanding applications. NNTHE BMB25 showcases impressive engineering with its robust steel construction and precision hydraulic systems. The machine features a 25-ton capacity with hydraulic cylinders generating precise, controllable force throughout the flanging process. The rotary table, machined to incredible flatness tolerances, provides the stable platform necessary for consistent results. Advanced servo-hydraulic controls allow operators to program complex forming sequences, adjusting pressure, speed, and position with remarkable precision. The machine's modular tooling system accommodates flanges from 100 millimeters to 2,000 millimeters diameter, and watch the magic happen as raw steel plate transforms into precision flanges. The process begins with carefully cut circular blanks positioned on the rotary table. Hydraulic clamps secure the workpiece, while the forming rollers, each positioned with micrometer precision, gradually shape the material. The flanging operation isn't just bending. It's a carefully controlled metal flow process that maintains material thickness while creating the precise angles required for leak-proof sealing. Advanced sensors monitor forming forces, automatically adjusting parameters to prevent material cracking or thinning. NNTHE real beauty lies in the consistency. Every flange emerges with identical dimensions, surface finish, and mechanical properties. Laser measurement systems continuously verify the flange face parallelism and perpendicularity, critical dimensions that ensure proper gasket seating. The machine's CNC control compensates for material variations, spring-back effects, and tool wear, maintaining tolerances within 0.1 millimeters across production runs. These flanges will eventually join critical pipeline systems, carrying everything from natural gas to chemical feedstocks. The precision we've witnessed ensures leak-free connections that protect both workers and environment. When you consider that a single flange failure in a petrochemical plant could cost millions in downtime and environmental cleanup, the importance of this precision becomes crystal clear. Here we witness one of machining's most demanding operations, boring and facing an 8-inch diameter hole through massive steel components. This isn't your typical drilling operation. We're talking about creating precision bores through materials that could stop a tank shell. These operations are common in heavy industry applications like hydraulic cylinders for mining equipment, gun drill operations for oil drilling, and cylinder blocks for massive diesel engines. NNTHE horizontal boring machine dominates this operation, with its massive spindle assembly capable of reaching several feet into the workpiece. The boring bar, itself a precision instrument weighing hundreds of pounds, must remain perfectly rigid while cutting forces try to deflect it. Advanced vibration dampening systems and precision spindle bearings ensure cutting tool stability. The cutting insert, a $300 piece of carbide engineering, must maintain its sharp edge while removing cubic inches of steel per minute. Setup requires laser alignment systems, ensuring the boring bar runs true within 0.0001 inches. And watch as the massive cutting tool begins its journey through the steel, creating that perfect 8-inch diameter bore. The cutting parameters are carefully calculated. Too aggressive and the boring bar deflects. Too conservative and productivity suffers. High-pressure coolant floods the cutting zone, not just for cooling but to flush away the continuous stream of steel chips that could jam the operation. The machine's CNC system automatically compensates for boring bar deflection, ensuring the final bore diameter remains within 0.001 inch tolerance across its entire length. Now comes the facing cut, creating that perfectly flat surface perpendicular to the bore. The facing head, equipped with multiple cutting inserts, machines the surface with feed rates measured in thousandths of an inch. This operation demands incredible rigidity as any vibration creates visible chatter marks on the finished surface. Advanced spindle balancing and anti-vibration tool holders ensure the surface finish meets hydraulic system requirements, where even microscopic imperfections could cause seal failures. NNTHE finish component undergoes rigorous inspection using coordinate measuring machines and precision bore gauges. The bore straightness, surface finish, and diameter consistency are verified at multiple points along its length. When complete, this component might become part of a mining excavator's hydraulic cylinder, where it will control movements of machinery weighing hundreds of tons. The precision we've witnessed ensures these systems operate reliably for decades, moving mountains one scoop at a time. Our final segment showcases the artistry of complex turning operations, creating intricate threaded components that combine multiple diameters, complex geometries, and precision threads in a single setup. These parts might appear simple, but they represent the pinnacle of machining skill, requiring perfect coordination of cutting tools, spindle speeds, and feed rates to achieve dimensional perfection across every feature. This component features multiple turn diameters, each with different tolerances and surface finish requirements. Notice the step-down geometry, requiring different cutting tools for each operation, internal threading that must align perfectly with external features, and complex radii that blend surfaces seamlessly. The CNC lathe setup involves multiple tool positions, each carefully programmed for optimal cutting conditions. Live tooling capability allows for off-center drilling and cross-hole operations without repositioning the workpiece. End mesh and end first. Rough turning operations remove excess material using aggressive cutting parameters and robust tooling. Progressive finishing passes gradually approach final dimensions while improving surface finish. The threading operation requires specialized thread cutting tools and precise spindle synchronization. The CNC system coordinates spindle speed with carriage feed to create perfect thread pitch. Tool changes happen automatically, each cutting insert optimized for its specific operation. Then single-point thread cutting tools carve helical grooves with mathematical precision, creating threads that will mate perfectly with corresponding components. Thread pitch accuracy within 0.0001 inches, proper thread form angles, and perfect surface finish all combine to create threads that exceed commercial standards. High magnification inspection reveals the crisp thread profiles that will provide reliable mechanical connection for decades of service. NNTHE completed part undergoes comprehensive quality control using specialized thread gauges, optical comparators, and coordinate measuring machines. Every dimension, thread specification, and surface finish is verified against engineering drawings. These complex turned parts often become critical components in aerospace applications, medical devices, or precision instrumentation, where failure isn't an option.